All right, hey, welcome everybody. I'm Chris McKitterick. I'm the director of the Ad Astra Center for Science Fiction and the Speculative Imagination here at KU. We're part of the Achievement and Assessment Institute, one of 12 designated research institutes at the University of Kansas. AAI and its centers partner with agencies to improve the lives of children and adults through academics, employment, career advancement, and building healthy environments, working to help children, adults, and communities succeed. This is our first public event. Thank you all for coming. And thank you for those of us joining us online, live or in the future. We hope to have this available later too. Also, a big thank you to the Lawrence Public Library for providing this lovely venue and for working with us to get the streaming tech up so those here can, not here can attend and participate. This is the first time anybody's tried this live streaming here, so this is fun. The Ad Astra Center brings together creatives, scientists, educators, and fans of speculative fiction to study and create work that changes the world. Through a rich series of expert talks, workshops, and masterclasses, social media, blog, video inspirations, and lots more. Starting with tonight's talk, we seek to build bridges between STEM and the arts by showcasing cutting-edge science and tech research and helping creatives engage with the forces changing the world. If you're a speculative fiction writer or want to be, check out our first AdAstranaut writing workshop series, starting with a weekend idea brainstorming and story development session. That's the weekend of September 10th to the 11th. It's the weekend after this. And then a weekend speculative fiction critique workshop 6 weeks from now. That's the weekend of October 15 to 16, where we'll help you revise your story into its best possible shape for its intended goal, whether that's publication or fanfic or whatever you want. Our events will be available both in person and streaming on our YouTube channel to increase accessibility for locals and those around the world. So tonight, we're going to hear from Dr. Philip Baringer about the Higgs boson in this particular universe, facts, speculation, and the story of a little ripple with a big bang. Phil has more than 25 years of teaching and research experience, both in the research field and using speculative fiction to examine those concepts. He's a professor emeritus of physics who's received numerous awards for his teaching, and I've had the honor of co-teaching our science, technology, and society class with him for years. Phil's an experimental particle physicist who has long studied the production of the top quark. He's a member of the Compact Muon Solenoid Collaboration, an international group operating an experiment at the European Organization for Nuclear Research's Large Hadron Collider. He believes in the importance of communicating science to a general audience. He's the lead faculty member of the University of Kansas QuarkNet Center, connecting the university's particle physics research group with local high school physics teachers and students. He's also received the Steeples Award for Service to Kansans, which recognizes faculty members for sharing their teaching and research with the people of Kansas. After Phil's talk, we'll take questions from all of you as well as folks online. Those who wish to participate in the upcoming AdAstranaut Speculative Fiction Writing Workshop have the opportunity to hear expert feedback from Mr. Baringer, who will be attending those as well. So without further ado, please give a warm welcome to Phil Baringer.
See if I can find the right button here to get the slides on here. There we go. Can you all hear me okay? Okay. So I'm going to talk to you about the Higgs boson in this particular universe. One of the reasons when I was talking to Chris about doing a talk for the Ad Astra series of talks, one of the reasons I focused on the Higgs boson is this is the 10-year anniversary of the discovery of the Higgs boson. The discovery was announced on the 4th of July in 2012, which to me seems like just yesterday, but I realize for, undergraduates at KU, that's what, they're probably still struggling with long division or something at the time and probably weren't terribly focused on the Higgs boson. But what I plan to talk about in the next half hour or so is, what is the Higgs boson? What is this thing? Why are all these people excited about it? Why should you be excited about it? What's been going on in the last 10 years? We've just been, lobbying for more Nobel Prizes. That's all we've been doing. No, there's been other stuff going on. And then, since these are people here interested in science fiction and speculation, we'll get a little speculative and talk about how the Higgs boson might connect to other issues in science. So this is kind of a standard graphic of the standard model that my colleagues in the physics department have seen ad nauseum. But it shows the Higgs boson as this white blob in the background. And I'll walk you through what this white blob signifies. So at the time it was discovered, it was the last one of these particles in the graphic to be found. All the other ones had been observed in experiments prior to 2012. The role of the Higgs boson, as we'll discuss in more detail, is to provide all the other particles on this graph with mass. And it was first postulated, the existence of this boson, in the 1960s, in the early 1960s. So this was not a quick find. It took people over 50 years to verify this theory that one of the people who came up with the theory name is Peter Higgs, and he got the Higgs boson named after him, even though there were other people who worked on the theory. Somehow he was the guy. So let me talk about the standard model that I referred to. It's our theory of particle physics. And to set the scale of things, you may have heard the phrase nanotechnology thrown around. Nanotechnology works on a scale. Nano is the 1/billionth. So 1/1 billion is the distance scale that you're talking about nanotechnology. So this is like really, really small. Nanotechnology is where they're manipulating like individual molecules and atoms to do stuff, and it's like super cool. But what we're talking about here is way smaller than that. So an atom is about 10 times smaller. So it's about 1/10 billionth of a meter is the size of an atom. And then the nucleus inside the atom is 100,000 times smaller than that. And then these particles we're talking about here in the standard model are at least 1,000 times smaller than that. I say at least because we don't really know how small they are. What we know is that they're smaller than 10 to the minus 18th meters. They're so small we can't measure how small they are. That's like the limit of our microscope's resolution, if you want to put it that way. So that's the scale of things we're talking about. And what our scientific program is to understand matter in sort of the most simple-minded way. Like, what are the tiniest bits that we can make matter out of? So this graphic shows you, like a brick or something, some piece of matter. And inside the brick, there's atoms making up the brick. And then inside the atoms, there's that little nucleus with electrons zipping around outside the nucleus. And then inside the nucleus are protons and neutrons that are making up the nucleus. And then we finally get to the scale of things that the standard model is talking about. There are things inside the protons and neutrons that are called quarks. So quarks and leptons, as far as we know, are the smallest bits of matter. Maybe there's something smaller and we just don't know. But that's what we're dealing with in this theory called the standard model. So here's this graphic again, and there's 6 types of quarks that we know about. There's 6 types of leptons that we know about. Those things in purple are a different kind of particle. They don't make up matter, but they create forces between the particles that do make up matter. And then there's the Higgs, which is kind of its own thing. So let me introduce you to the forces that we deal with. There's a force called the strong force. We have these super imaginative names for these things. The strong force is what holds the nucleus together. Okay, so it's very strong at nuclear scales, but it's kind of, we don't notice it at all on an everyday scale. It's just sort of confined to those really small distances. The electromagnetic force is one that we deal with both in atoms and in everyday life. Electricity, magnetisms, all that stuff is coming from the electromagnetic force. And then, since there's a strong force, there's also a weak force. That's a force that, again, is only noticeable in like nuclear scale interactions, everyday scales. We don't really notice it, but it's important in that it's responsible for some nuclear processes that cause nuclei to decay, and it's also part of what goes on inside the sun to make the sun shine. So we like it that the sun shines, and the weak force is part of that. So the standard model is a theory. I'm an experimentalist, so I'm on shaky ground when I talk about theory, but I see another experimentalist here, but I don't see a theorist here, so I think I'll be okay. We'll see. Anyway, the mathematical framework for the standard model is something called quantum field theory. So we're dealing with small things, right? So there's a couple of reasons that Newton's physics, our physics of everyday things, doesn't work. One reason is we're dealing with small things, and that means we have to get into quantum mechanics, which was developed to understand atoms. And these particles are also going rather fast compared to the speed of light. And when things go rather fast compared to the speed of light, we need Einstein's special relativity. So when we need both of those things, we wind up with something called quantum field theory, which was sort of developed in the mid-20th century. So what we call the standard model is actually a collection of 3 quantum field theories, one for each of those 3 forces, the strong, weak, and the electromagnetic. Why should you believe any of this nonsense? Well, we test these ideas. The first quantum field theory that was developed was the one for electromagnetism, and that goes by the name quantum electrodynamics, or QED. When a physicist hears QED, he's probably hearing something different from what you may hear when you hear QED. But this is one of the most accurate theories in the history of physics. I just threw up an example here of a paper talking about the electron magnetic moment. Let's not worry what that is, but it's something you can calculate in the theory, and it's something you can measure in the lab. And let's see, does this thing have a pointer on it? Oh, that was the wrong button to push, clearly. Yeah. Oh, there we go, I've got a pointer. Okay, so here's like a ridiculous number that this is like, when your 5th grader just writes down all the numbers that were on the calculator rather than being sensible and truncating it. But these are all significant digits. So this was measured and agreed with theory to a ridiculous number of digits. So here's a little outtake from this article where the things are measured to 1 part in 10 to the 12th. So 1 part in a trillion. And the theory is getting it right to that precision. So something's got to be right with this thing. All right. Okay. That would be like a huge coincidence that you get all those digits correct. Physicists are very proud that this theory fits on a coffee mug. Coffee had a lot to do with the development of this theory, as you can imagine. Now they're very proud of this, but this is a really cryptic and compact mathematical form that you need to use to squeeze it on a coffee mug to make it something more understandable by a normal person. You would need a lot, like pages of stuff. But anyway, theorists are very proud that it fits on a coffee mug. So let's go back to 2012 and the discovery of the Higgs. So there's a picture of Peter Higgs, and there's a picture of the Large Hadron Collider, which is a big accelerator near Geneva, Switzerland. So if you're flying to Geneva, you will not see this red thing on the ground that was put on top of the photo, but just to show you where this thing lies. And the little names, CMS, LHCb, Atlas, those are experiments that are located at different locations around this ring. So some trivia about the Large Hadron Collider, for those of you who like facts and figures. It's 27 kilometers around. I'll let you do the conversion to miles. It's 100 meters underground. So you can be driving along cornfields in France and not know that you've got 100 meters down this big accelerator underneath. It collides protons, and that's what it was doing when we discovered the Higgs, but my nuclear physics colleagues at KU also use this machine to collide like lead nuclei and make a big old mess. This has been taking data since 2009. For the Higgs discovery, it was running with a collision energy of 8 trillion electron volts. So trillion electron volts is a lot of electron volts, and this is the highest energy accelerator that has ever been constructed. The one prior to that was at Fermilab just outside of Chicago. It was called the Tevatron because it ran with beams of 1 TeV, so 2 TeV collisions in the center of mass. So this was like 4 times more energy when we discovered the Higgs, and later it increased the energy to 13. Just this year, it increased to 13.6. So we're at a new energy regime just this year. Its design energy is 14, but so far all the engineers haven't been able to work all their magic to get it quite up to a full 14 without being in danger of wrecking the thing, and so they don't want to wreck it because it costs a lot of money. So we're colliding these protons together, and then we have these detectors that look at the stuff that comes out. This is a representation of particles coming out from one of these collisions between 2 protons. The little red things are there to show you a couple of photons coming out. So a photon is a particle of light. In this case, they're like gamma rays. They're not like the nice friendly light that comes out of this, but gamma rays you don't want to be around. They're nasty and will hurt you. But nonetheless, they're just part of the electromagnetic spectrum. And one of the signatures of the Higgs boson is it will decay into 2 photons. Now, that you don't look for the Higgs directly because it lives for something like 10 to the minus 24 seconds, some ridiculously short lifetime. So it's not around long enough to measure the Higgs itself, but you look for the debris that came from its decay, and then you try to piece the pieces together. So this is the only technical data slide I'm going to show you, but I just want to give you a sense of how you put the pieces together. So basically, you look for a couple of gamma rays coming out, and then you're like, let's imagine these gamma rays came from the decay of a Higgs boson. Okay. What would the mass of that Higgs boson have been if these 2 particles had come from that? And we know how to calculate what the mass would have been because we've got all that energy and we can figure that out. So what this is a graph of the hypothetical mass of the parent of the two photons. And typically, these are just two photons that had nothing to do with each other, right? So you would just get some random number when you did that. So most of what you see here is just some random number. But here, some stuff was starting to pile up at a particular number. So this bottom plot is the same plot, only trying to deceive your eye and make you think this is more important than it really was. But you can kind of see that, okay, there's this blip here that suggests that maybe there was something with a mass of 125 that gave us a couple of photons. So this would not have, gotten you to, announce a discovery, but there was a second independent experiment that was seeing exactly the same thing at exactly the same place. And there was another channel. The Higgs boson can decay in a lot of different ways. And we also saw the same thing when it was decaying into a couple of Z bosons. So we had basically 4 independent measurements showing us the exact same thing. And when you put all that together back in 2012, it met the criteria that physicists have for announcing a, quote, discovery. And for statisticians, that threshold is 5 standard deviations, which if you didn't do something funny, then that means there's, I don't know, like a 1 in a billion chance that this was just a coincidence. So with the Higgs, now all these pieces of the standard model had been experimentally observed. Just to give you a little bit of history, I started in the field in the early 80s. And so in the course of my career, the W and gluon, which are 3 of these force carriers here, were discovered in the early 80s. And then at that point, the only thing were this thing called the top quark and this thing called the tau neutrino. And they fell in line. Fermilab discovered the top quark in 1995, and donut experiment, I just love that acronym. Somehow they worked something out. Nu is standing for neutrino and T is for tau, and I don't know what the D and the 0 are, but the donut experiment discovered the tau neutrino. So I showed you that one thing where quantum electrodynamics was making these predictions that were verified by measurement. And the standard model as a whole has made gobs and gobs of predictions of things like reaction rates, how particles will decay, how momentum and energy will be spread around. And all of these things have been verified over and over again by experiments. It's an incredibly successful theory. So what have we been doing since the Higgs discovery? We've been studying the Higgs. It's like, we have a new toy. Let's look at it. Let's take it apart and see how it works. So I don't expect you to read all of this stuff on here, but if one of these red data points lines up along that dashed line, it means that our measurement agreed with the theory prediction. Okay. So we've made gobs and gobs of measurements, and they're all lining up with the theory prediction pretty nicely. So it looks like this thing that was discovered in 2012 is indeed described by the theory of the Higgs boson in all its particulars. So what's so special about it? This first one is a little technical. It's the only one of the particles on that table that doesn't have any spin. So most particles have what's called an intrinsic angular. Protons have it, all the quarks and leptons have it, the carriers have it, this one doesn't. Okay, it's a 0 spin elementary particle, which makes it unique. The Higgs boson is evidence of a Higgs field that permeates space. So what do I mean by a field? You probably heard of gravitational fields, right? If I drop something in here, it will fall to the ground. And one way of phrasing that is there's a gravitational field in the room that interacts with the object and makes it fall to the ground. So there's fields for all kinds of things, for electric fields, magnetic fields. So in quantum field theory, there's that word again. Fields can have chunks appear of the field, and those chunks are particles. So the Higgs boson is really a chunk of the Higgs field that manifests as a particle when you disturb the field. Now, the Higgs field gives the other particles in the standard model mass when it interacts with them. It's sort of, it's like, you know, if you drop a marble through some molasses or something, the molasses slows it down as it falls. The Higgs field is like the molasses. Different particles have different masses, so for some it's like water rather than molasses or something. It doesn't slow it down as much, but the field slows down particles, gives them mass. Now, to give some love to my nuclear physics colleagues, this is where they would say, now hold on. Most of the mass in this room has nothing to do with the Higgs boson. It has to do with nuclear physics. And they're right. So most of the mass in this room has to do with the nuclei in your atoms. And the nuclei are made up of quarks, and the Higgs gives mass to the quarks. But the quarks have a lot smaller mass than the proton itself. Most of the mass of the proton is coming from the strong force field that's binding the quarks in the proton. So it's the nuclear force that's giving you most of your mass, and the Higgs is giving you some tiny percentage of your mass. So it's about a factor of 5, I think. Another thing I like to point out is that the Higgs theory doesn't explain why different particles have different masses. So an electron has a really different mass from a top quark or some other particle in the standard model. In the theory, there's just like a number that is in the technical word, it's the Higgs coupling to the particle. So instead of just saying the electron has a mass of, you know, half an MeV or whatever, you say the coupling of the Higgs to the electron is blah. So it just puts off the issue that we don't know how to explain the masses, okay? We know the Higgs is giving it a mass, but why that mass, we don't know. Lastly, to my mind, the discovery of the Higgs is first and foremost a victory for math. Okay, yay math. So here's my yay math slide. So this again gets a little technical. Quantum field theory really prefers its particles not to have any mass. It's like really, really happy if particles don't have any mass at all. And if you try to give them mass, it gets unhappy really fast. Quantum field theory, like quantum mechanics, predicts probabilities. Okay, it predicts the likelihood of something to happen. And a probability should be a number between 0, this will never happen, and 1, this will always happen. And as I say here, you know, coaches give you 110%. Mathematically, that makes absolutely no sense. Sorry, coaches. It's got to be between 0 and 1 if it's a probability of something happening. Without the Higgs field, if you just tried to give particles mass in these quantum field theories, you would start getting ridiculous numbers out of the theory. It would start predicting, oh, the chances of that happening are 1 billion. You're like, well, that can't be right. It's not supposed to be bigger than 1. What? So what Higgs and some other theorists did is they cooked up a way that the math would work with massive particles. This is a really like super mathy thing that they did in the 60s. And that predicted there'd be this weird particle that was left over after you did all the math. And lo and behold, 50 years later, we found this particle. So math is just like weirdly effective in, in describing nature. Anyway, so that was the part of the talk that was, to my mind, on pretty solid ground. As an experimentalist, I can get up here and defend all the stuff I said to you, pretty thoroughly. But, the subtitle was Facts and Speculation, so we're done with the facts and let's go on to the speculation. The question you might ask is, okay, the Higgs mass, does that mean the Higgs has something to do with gravity? The short answer is no. The longer answer is maybe, possibly, perhaps. So, again, if you've had physics in high school or college, you may be aware that there's not just one kind of mass, there's two kinds of mass. One kind of mass is called inertial mass, and that's like this astronaut in the middle of space is trying to push a heavy object and a lighter object. And if you give the same push to the heavy object that you give to the light object, guess what? The light one's gonna go faster than the heavy one. So inertial mass is if you give something a push, how much is it gonna resist that push? The other kind of mass is gravitational mass, which is, if I drop this thing, it's going to accelerate towards the Earth. The Earth is exerting gravity. So it's how an object interacts with gravity is gravitational mass. And this is just reminding you that you have the same mass on the Earth and the Moon, but you're gonna weigh a lot more on the Earth because Earth's gravity is a lot bigger. Now, Einstein's general relativity makes these two kinds of mass equivalent. That was kind of his starting point for the theory. And from that came all sorts of bizarre stuff, which we'll get into in a second. But the Higgs boson is basically giving things inertial mass, which at least conceptually, it would be a leap to go to gravitational mass. Okay, quantum field theory doesn't play well with Einstein's theory of gravity. The reason for that is quantum field theory uses what's known as a flat space-time. And Steven Weinberg, the late great theorist, said quantum field theory is the way it is because with certain qualifications, there's always qualifications, this is the only way to reconcile quantum mechanics with special relativity. And quantum field theory has flat space-time. So flat space-time is the kind of geometry that you're used to from, high school geometry. Euclidean geometry means if I start out with parallel lines, they stay parallel. Okay? If I'm walking east and you're walking east a few feet away, we both keep walking east and our paths never cross. Okay? That's flat space. Einstein's theory of gravity uses a curved space-time. In his theory, mass distorts space so that it's no longer Euclidean. So a two-dimensional example of that is if you and I start in parallel paths and walk null, okay? So that's because we're moving on a curved surface. So quantum field theory doesn't play well with curved space-time. So we've got Einstein's theory of gravity over here with one mathematical scenario and quantum field theory over here with a different mathematical scenario, and they don't talk to each other. Okay, or they don't play well with each other very well. Now, people have come up with schemes for combining quantum field theory and Einstein's gravity, and that leads to something called string theory that people like Brian Greene are always talking about. which has the lovely feature that you have lots and lots of more spatial dimensions. We live in a world where we think of 3 spatial dimensions, right? This way, 3 spatial dimensions. There's like 10 or 11 in string theory, and instead of particles being represented by little points in space, they're represented by little stringy things in multiple dimensions. Okay, so this is a language that combines the two, but at a cost of lots of other stuff going on. Okay, I am going to get back to the Higgs here, but I'm sort of laying out some gravity things for you. Some other fun thing, our astrophysics friends tell us there's this stuff called dark matter and dark energy in the universe. They also tell us that all of this normal matter that we particle physicists have been working so hard to understand makes up 4% of the stuff in the universe. And this is just one more example of these darn astrophysicists trying to make us feel bad. Okay? You know, we started out a while ago, the Earth is the center of the universe. Yay, us. Then like, no, the Earth is not the center of the universe. But we're around a very special star, right? The sun, it's the best. No, the sun is just this mediocre star out on the edge of the galaxy. But ours is the one and only galaxy, right? No, there's bazillions of galaxies. You're just one. It just goes on and on. And all this matter that we've worked so hard to study, it's like 4% of the energy budget of the universe. Thank you very much, astrophysicists. Dark matter was discovered because you can study the motion of galaxies and other objects that are emitting light and see that they're not moving the way you expect them to. You can calculate how you expect them to move by, we understand gravity, right? And so there's something out there that's causing a whole bunch of gravity that we can't see, and that's why it's called dark. So dark matter is this material that's causing gravitational effects, and we don't know what it is. Dark energy was discovered in the late 90s. People were looking at the expansion of the universe. So, galaxies are flying away from each other ever since the Big Bang. The universe has been expanding with galaxies getting farther and farther apart. And there was a study in the 90s that showed that it wasn't just like there was one big bang and then things have been coasting from there, but things are accelerating. So something is continuing to push galaxies apart. There's this pressure in empty space that's pushing things apart. And that's given the name dark energy just because, I don't know, I guess dark matter, dark energy goes with dark matter. But anyway, we don't know what the heck that is either. So most of the universe's stuff, we don't know what the heck it is. Yeah. The names are great, right? But okay, so any connection of any of this with the Higgs, this is where it gets speculative and all kinds of people have all kinds of ideas. So one thing you can say for sure is dark matter ought to have mass because it's affecting things by gravity, and things with mass affect things by gravity. The Higgs is supposed to interact with things that have mass, so you would think the Higgs would interact with dark matter. Okay. So possibly the Higgs may serve as some kind of bridge between the ordinary matter that we know and love and this dark matter, whatever it is. And there's all kinds of ideas about that. And we've been using those ideas to look for dark matter emerging from the collisions of the Large Hadron Collider, and so far no success. There's lots and lots of other ways that people look for dark matter that don't involve big colliders, but that's a very active program trying to pin down what that stuff is. Okay, to discuss the Higgs and dark energy, we must first discuss the vacuum. The vacuum is nothing, right? Empty space. Empty space is not empty. As we just said, whatever is creating dark energy is in so-called empty space, and it's exerting this pressure, pushing things apart. Some people attribute dark energy to something called the cosmological constant, if you want another buzzword. That was something that originally appeared in Einstein's equations of general relativity, his theory of gravity, and he had it in there because he wanted the universe to be static. And then, like, Hubble and people told him, no, the universe is expanding, Einstein. And he was like, oh, crap. And he crossed out the cosmological constant, and now he could get an expanding universe from his equations. Well, now that we know that the universe is accelerating, you can put that cosmological constant back in Einstein's equation and use it to make an accelerating universe. And what that basically means is a pressure coming out of empty space. So that's the gravity side of things. Let's go to the quantum field theory side of things. In quantum mechanics, the vacuum, empty space, can have energy. Why is that? If you've read about quantum mechanics, you may know that it predicts things like energy levels in systems, like, you know, these are the energies that electrons can have in hydrogen atoms and things like that. So in some systems, the lowest possible energy allowed by the rules of quantum mechanics is not zero. Okay? In everyday physics, you know, you can get to zero energy, just take all the energy out. In quantum mechanics, there are some systems, and one is a really basic system called the harmonic oscillator, which is, you know, like a little pendulum or something, that cannot have zero energy in quantum mechanics. The quantum vacuum is full of all these fields that we talked about, the strong force, the weak force, the Higgs field, all this stuff. Plus there's virtual particles bubbling up that we haven't talked about. Particles can appear and disappear in the vacuum. And all of this stuff doesn't necessarily have a lowest energy of zero. There might be a non-zero energy to some of these things bubbling in the background of the vacuum. In particular, the Higgs, in order for the Higgs field to work as advertised and give particles mass and function as it's supposed to function in quantum field theory, it has to have a non-zero, what's known as vacuum expectation value. So it has to give energy to the vacuum for the Higgs to give particles mass. So these are two completely different mathematical paradigms, both talking about there being some energy in empty space. And you would hope that when we get a theory of everything that connects up gravity and everything, that somehow it would connect this quantum field theory vacuum with dark energy. And people, of course, have gobs of ideas, but nothing definitive. So here's another take on vacuum expectation value. What would you expect your vacuum to be worth if you sold it on, anyway. Okay. So I got to give you a doomsday scenario here. This is a good one. It's probably not the doomsday scenario that you all are most worried about these days, but it's possible that the vacuum is not stable. Okay. In the early universe, you know, the whole universe was in a hot, dense state. Big Bang Theory fans out there, we can all sing the song. The whole universe was in a hot, dense state. Yes. And then things cooled off, and the Higgs field relaxed into some sort of valley of its allowed energy. It's going to sink to the lowest part of the valley that it can, just like, you know, a ball going down a hill. It's going to settle down at the bottom. It's possible that there's a lower valley, though. The Higgs may have settled into this valley over here, but the lower valley is over here. And if there's a lower valley, then this may be what's known as a false vacuum. And if it's a false vacuum, it could someday go down into the lower vacuum. So look for false vacuum decay in your online search engine to be thoroughly terrorized. If the universe were to drop into this more stable state, then that would change the laws of physics. And that most likely would not be good for us. It most likely would be really, really bad for us and everything around us. So for science fiction fans, there's a number of science fiction writers that have used this. Jeffrey Landis, I just rediscovered a short story of his called Vacuum State that uses this idea. And Greg Egan, who writes all this super hard science fiction with lots of equations, he's used this in one of his novels. So the Higgs is key to whether the vacuum is stable. And this is a plot that some theorists cooked up. I'll walk you through it. So the key things as to whether the universe is stable is the Higgs mass and the top quark mass. Why the top quark mass? Because the top quark is the heaviest elementary particle that we know of. Okay, so it stars in this show. So this is the top quark mass, this is the Higgs mass. This little dot here is our current best measurements of those two numbers. And it lies in this yellow region here, which is not green, stable. It's not red, completely unstable, but it's metastable, which means that the lifetime is probably really long, maybe billions of years, but it might not be forever. Now there's gobs of assumptions that you can question and argue with that go into this calculation of stable regions and metastable regions. And so I personally don't stay awake at night worrying about this. There's a reason this is in the speculation part of the talk. But if you're looking for a doomsday for your science fiction novel, this is one possible scenario. Now let me lead you even farther off the deep end. Okay. One thing people worry about with the Higgs is something called fine-tuning. The standard model has lots of numbers in it, the masses of all these particles, the strength of all these forces, and they're not anything that the theory predicts. It's just things that we go out and measure, and then we plug them into the theory, and then the theory can predict some other things. One of the parameters that really worries the theorists ever since we found the Higgs is they're like, wow, 125, even though it's the second heaviest particle we've ever found, they're like, wow, that's so light. How did it get so light? And they worry about the numbers being fine-tuned so that all sorts of things magical happen with a Higgs at 125. And some other parameters like the strength of the strong force and the relationship between gravity and electromagnetism, if any of those were just slightly off, chemistry wouldn't happen, nuclear physics wouldn't happen, life couldn't exist, we wouldn't have galaxies, we wouldn't have stars. So there's all kinds of things that you can claim are fine-tuned about the universe, and these numbers have to be just exactly so for us to be sitting in this room talking about it. The hope is that there'll be some theory of everything that will explain why these numbers are the way they are, and then we can all relax and go, oh, now we understand. Unfortunately, our current theory of everything, string theory, people at first thought, oh, string theory will explain all these numbers and why they're the way they are. No. String theory allows for just any old kind of universe. Any old kind of universe you want to think of, string theory is good with that, okay? It's not picky about these parameters at all, and this was a huge disappointment to the theory community. So what do? Well, this is sort of the theory equivalent of punting on 4th and long. You can say, there are many, many, many universes, like string theory tells us. You can have any old universe. And the reason things look so finely tuned to human life in our universe is that, hey, it's selection bias. We're in a universe with people. There's lots of random universes out there, but we just happen to be looking at the one that has people in it. Okay. So an example of selection bias is, we're in a room at the library, and I'm like, everybody in the world goes to the library because I spend all my time at the library, and the only people I see are at the library. So I have this library principle that I can apply, that all the people in the world are at the library. But it's my selection bias. Just because I spend all my time at the library doesn't mean every person does. Just because I live in a universe that has these laws of physics doesn't mean every universe has to have those laws of physics. The phrase anthropic principle gets thrown a lot in this context. And, to my mind, that's not so much a scientific principle as kind of an excuse, but one thing I will say, it is perfectly valid to use as a data point that people exist, okay? That's a perfectly valid data point. But now we're in the multiverse, okay? Nobody ever uses multiverses in science fiction and fantasy, do they? That's a completely new concept. Good news, there's multiple multiverses. Cosmologist named Max Tegmark identifies 4 different types of multiverses. Brian Greene identifies 9. I'll leave you to form your own taxonomy of multiverses. The kind of multiverse we were just talking about to explain away things with string theory is where there's different laws of physics in different universes. And our universe is 3 dimensions of space, 1 dimension of time. And in string theory, our universe could be floating in 11 dimensions of space. And next door are other universes with other laws of physics. And they talk about membranes, where our universe is on this membrane and the neighboring universe is on that membrane. And all the universes are out there in this gigantic multiverse. That's sort of the string theory multiverse. A somewhat more mundane universe, or multiverse, is they're all just 3-dimensional and they all have the same laws of physics. And they might have different distributions of matter and energy. Galaxies might look different in this other universe or something, because they might have started out with different initial conditions or something. But the laws of physics are all the same, and we're all 3-dimensional. And this comes from the cosmology idea of inflation. You can look up eternal inflation for fun. This is not something that the Fed is going to be able to do anything about. This is just something that's in the universe. So the idea of inflation is, in the early universe, things were expanding, but then they just inflated really fast, like someone inflated a balloon really fast, and things got far apart from each other really fast. And eternal inflation is, this is still going on. Like, the universe is more than just our section that we can see. Some other universe that inflated over there, and another universe that inflated over there, and all these little baby universes popping up everywhere. So this is another, making us feel bad. It's like, this isn't our only universe. It's just the only one that we can see. There's gobs of universes out there. We're not that special. So a completely different kind of multiverse is the quantum many worlds multiverse that you may have heard about. There's this explanation for probability in quantum mechanics. In quantum mechanics, something may have a 50-50 chance of happening, like, the cat being alive or dead in the box, or, whatever metaphor you like. Well, either you have to accept that the universe, in the jargon, collapsed into one state where, the cat was alive, if you want the cat to be alive. Or there's one universe where the cat came out alive and one universe where the cat came out dead, and things split at that point. And now you have two universes, one where the cat lived and one where the cat died. And so as you can imagine, there's like every time there's some quantum decision made, the universe splits and splits and splits. And this is the quantum multiverse, which has been used in a lot of science fiction. These multiverse ideas are difficult, perhaps impossible to test. It's like, how do you get to this other universe and check it out? I don't know. All right, so we've gone as crazy as we can get. Let me summarize. The Higgs boson was discovered 10 years ago at CERN's Large Hadron Collider. Since then, we've been studying this beast, and it seems to conform to our theory. There's still a lot we don't know and can speculate about. How does quantum mechanics and all this particle stuff connect to gravity? What's the nature and stability of the vacuum? Are there multiverses? Maybe you all can tell me. Some of this may be fertile ground for fiction. Right. Thank you all for listening to that stuff.
Thank you very much, Phil. I have all kinds of ideas now, and I have some questions for you. By the way, before we move to the Q&A portion of this, we have some people on YouTube watching. We have some folks on our Discord, and of course, y'all. I also wanted to thank the Ad Astra Center's research assistant. I'm pointing to him back here. This is Logan Edmondson in the tech cavern.
The man behind the curtain.
He's operating the cameras and video and making sure everything actually works. I'd also like to mention that Neil Kingston, the director of AAI, our parent organization, is here tonight. So, does anybody have any questions for tonight's speaker? I have a ton here, but I want to hear from you all first.
Thank you for your talk. Yeah, so thinking about fine-tuning, do you think it ever won't be a problem, or will we ever find answers, and will it all make sense, or is it evidence of other things?
That's a great question. Because, yeah, you can imagine it being a continuous ongoing problem, right? Even if, there's ideas like that you know very well of supersymmetry, which would, if there's these supersymmetric particles out there, that would explain away some of the fine tuning, but then it would probably just move to something else, right? Why are these parameters like that? So, yeah, I mean, I understand. I'm not a theorist, right? So I don't have this same sort of mindset of understanding these subtleties of the theory, but I would imagine there'd always be subtleties that people would be worried about. I don't know. What do you think? What's yeah. Right.
So on the Discord, we have a question here.
Yeah.
Can you say something about loop quantum gravity?
I cannot. It's there's. I'll say something very brief, but I really don't know a lot about this. There are theories of quantum gravity that don't go all the way to string theory, that are sort of attempts at sticking quantum mechanics into gravity that don't go all the way to 11 dimensions or what have you. And so that would be in that category of theories that, I'd have to Google it to remind myself what that particular theory is about. But yeah, it's certainly fertile ground for exploring and speculation.
Thank you. That was so great. I think I took a class with you 20 years ago before the Higgs was discovered, so it's amazing to see how your presentations have updated over the course of these changes. I'm curious, do you read science fiction, Dr. Baringer?
I read a ton of science fiction, yes.
Who's your favorite?
Oh, I can't say because there's authors in the room and what's.
Oh, I see. Okay, we wouldn't want to
Chris,
offend
of course,
anybody.
is my favorite author. Is Kid here? What's
Maybe a better refinement of my
Oh.
question is, what science fiction do you read that lines up with your discipline that you find really interesting and meaty in an exploration of what you study?
Yeah, so to give you a more general answer to your question, I tend to read more science fiction than fantasy. And in science fiction, I tend to read more of the harder, more physicsy kind of science fiction. Yeah. Space opera, you know.
So you're mentioning Higgs boson as a triumph of math, and I know you layman's reading, Wikipedia reading, that some of the other quarks are found by having good mathematical parameters you were trying to discover.
Right.
Do they have those parameters for dark matter, or are they kind of shooting in the dark right now?
So one of the things about dark matter is it's really kind of unconstrained what the mass of it is. It could be like super small, like, you know, in particles we know neutrinos have super small mass. It could be way down there. It could be gigantic. And the way you search for the dark matter depends on what mass of dark matter you're looking for. So like the Large Hadron Collider, we're looking for dark matter that's pretty massive. We're not going to see the light stuff very easily there. But other experiments, like they go down in mines and look, you know, get themselves shielded from all kinds of disturbances and look for little disturbances of the force, and you know, that would be looking for the lighter dark matter. So there isn't a lot of guidance on that. Yeah. In terms of writing your fiction, you can go however you want, but you know, it's like you know, like I said, once I say what the Higgs mass is, then the theory tells me all about it. Once I say what the dark matter mass is, then there's consequences to what that mass would be.
Phil, I'm sure you've heard those wacky ideas about operating the Large Hadron Collider might create a black hole, consume the Earth, or open a portal to hell. What are your thoughts on these ideas? And also, what kind of energy would it take to actually create something like that?
So we are probably less likely to do that colliding protons than the nuclear physicists are colliding, you know, big lead nuclei, creating something really hot and dense. And we quite seriously have been looking for mini black holes to emerge from collisions at the Large Hadron Collider. That would be really cool in that it would give us a definite connection between our particles and gravity, because black holes are a gravity thing. The idea of that being, you know, you get a black hole if you get dense enough matter. So if you get enough matter in one little locale by smashing things together, maybe you can make a little black hole. Why are we worried about that not eating, you know, we're not worried about that eating Geneva, because the little black holes would evaporate really fast if we believe Stephen Hawking, right? So that there's this thing called Hawking radiation where black holes evaporate by spitting out particles. And if the only kind of black hole we could make is something that would evaporate really fast. Nuclear physicists also worry about something called strangelets, which involves strange quarks and changing the nature of the nuclear matter in a funky way. The basic argument for not worrying about any of that is, as proud as we are of our, you know, 13 trillion electron volt collisions, every day there's cosmic rays with more energy than that smacking into us. And people have done calculations of what would it take to make the moon disappear, you know? And the fact that the moon hasn't disappeared because all these cosmic rays are smacking into it are like, we don't have to worry about the Large Hadron Collider, the moon's still there. So if you look up one night and the moon is like fizzing out, then get worried. But I don't know. Yeah.
I've been reading several Brandon Morris science fiction novels recently.
Uh-oh.
He works, I don't know if you're familiar with his work, but it overlaps
it.
with the kinds of things you're talking about. Since you don't, you probably can't answer this question. And just in case he's in the room, I don't think so. You might not want to. Anyway, I want to know if his physics held up.
Yeah, no, I'm not familiar with that, but
He's got about 20 or 30 books out.
Okay.
Several of which are in this film.
nice. I'll have to check that out. Yeah, I mean, different writers care about physics more than others, and different editors care about physics more than others. I remember Chris had his award-winning story in Analog, and they were giving you a super hard time about the physics in your story, right?
I worked it out after like 6 years of math.
Yeah,
And your help.
but other editors are like, we don't give a crap if it's a good story. Who cares if the physics is right? But sometimes if the physics is really bad, it'll throw me out of a story. That tends to happen more with like movies or TV shows for me than it does with written science fiction. But yeah, I'll have to check this out and let you know.
I assume that since the discovery of the Higgs boson that we've continued to observe more of them. Is it to a point where that's like kind of common, or does it still feel pretty special when they get observed?
It's pretty common now. I wouldn't say it feels routine yet, but it's getting there. And when we upped the energy from 8 to 13, that really upped the rate at which they were being produced quite a bit. So it's like turning the nozzle so that the water's coming out faster. One thing I'll just as kind of an aside, in my career, I was also at Fermilab when the top quark was discovered in the mid-90s. And that first top quark paper, there were like 6 top quarks that we'd found. And then you get to the Large Hadron Collider, this much larger energy, and they were producing like tens of thousands of top quarks a second. I was like, holy cow, this was like a really big mind shift for me. And we're not quite at that extreme with the Higgs, but it's kind of getting more routine. We still wish we had more statistics to measure some things that are rare. That's why they're planning on running the Large Hadron Collider for like another 20 years if they keep getting funded. So
thinking like a writer here, trying to imagine what the experience of being there is like. What's it like to work in the Large Hadron Collider facility, like in other particle accelerators? Like the physical experience, what's that like?
So to me, the most fun part is the international environment. Like you go to CERN, and our collaboration has like 3,000 collaborators in it from all around the world. A lot from Europe, as you would expect. About a third of the people in my experiment are from the US, but there's people from Asia, from South America, from everywhere. And you go to the CERN cafeteria and there's all these languages being spoken, but everyone is also speaking the same language of physics. So, someone who grew up in a wildly different environment, you sit down and talk about, the latest data on the Higgs boson, and you're like totally on the same page, even though, that this person is from a different part of the world with wildly different. So to me, that's the coolest part. The physical facilities are pretty grungy. They don't put a lot of effort into their physical facilities. I mean, the machines themselves are like beautiful and expensive and intricate and state of the art, but you're like, go sit in that desk in the corner. No, there's no air conditioning, and no, the toilet doesn't work, and you know, it's like, you know. So that part isn't so special.
Got a question here from
We
YouTube.
had a meeting room at Fermilab that was called the Ninth Circle. So like the Ninth Circle of Hell. So, you know, just to tell you how people regard these things.
Is it that bad?
What's that bad?
David on YouTube says, we touched on this a little toward the end, but is there any path forward for testing multiverse theories?
It would take an incredible amount of luck. I mean, people who think about this harder than me may have a better answer, but what could happen, which would probably not be good, is, you know, in the scenario of the multi-dimensions, there conceivably a couple of universes could collide. And that probably would not be good, but you would notice it. Similarly, if you know, if there's just like another bubble universe in our three-dimensional universe, there could be some means of detecting that indirectly through, I don't know, some sort of radiation or obvious quantum fluctuation or something like that. But that, you know, that's like super speculative. As for, you know, the Hugh Everett quantum mechanical multiverse, there's like no chance of that, even though that's the most popular thing to do in science fiction, right? Is you go and meet yourself that made this other decision back when you were 8 years old, and you know, I see no physical way that's happening, but makes for great stories.
So but you would observe from the interactions. Could that be going on right now and have some
Yeah.
sort of, okay.
Yeah, it could be going on right now.
Would that maybe explain the dark energy or something like that?
Yeah. That sounds like you may have a story there.
What does the experiment look like? What would you?
Well, I think it would look like an observation, right? It wouldn't be an experiment, but it would be a astronomical observation. You'd see something funky happening in the universe out there.
I just want to kind of build on what Chris was asking for, because we want that sensory experience.
Yeah.
Like Carl
Yes.
Sagan was talking about how when you're doing radio astronomy, you're not, unlike what the movie shows you, you're not sitting there plugged into the thing. You're sitting at a computer and something bleeds.
Right.
When you are in CERN or whatever,
Yes.
and you discover the Higgs boson, is it you're sitting there and you see the whole thing light up and there's all sorts of cool lights and
Yeah,
stuff
yeah.
and alarms, or is it your computer goes bleep?
So there are cool control rooms that you know, not quite Bridge of the Enterprise, but you know, all kinds of screens all over the place, and a room with a bunch of people working at their stations, and so that there's a control room for the accelerator, and then there's control rooms for each of the experiments, and so you can see on different screens, you know, how different parts of your detector are behaving. You can see on different screens, you know, pictures of collision events as they occur. They'll pop up on your TV screen. So yeah, I shouldn't undersell that, because that's actually a lot of fun to be on shift, and you're watching all these screens at 3 a.m. and seeing data come in. In order to find something like the Higgs boson, though, you've got to sift through piles of this data, what I'll call offline. So what I'm describing is online, while you're taking data, watching things coming in and monitoring it. But it might be years later, after you've recorded that data to, you know, some many petabyte thing, and you've sifted through it, and you know, that's going to be you at your laptop, you know, writing code and bringing up plots of what you're sifting through the data, and then, you know, if it's a really good day, you'll be like, oh, this could be interesting. Visual tools for sure. And if I'm looking for the Higgs boson, I'm actually not supposed to look at it, right? You're supposed to do a blinded study so that you don't bias yourself. Like, oh, if I remove this data and just look at this data, then, oh, I've got a nice signal here, right? So you've got to try to unbias yourself as much as you can. And then, when the day comes that you think you've optimized your analysis, then the collaboration may decide it's time to unblind, and that's where if you see something, you're like, holy cow, there's something there. And that's really cool.
I got a question here from YouTube saying, how often does bad science completely take you out of a piece of media or a story? What do you do with that?
Quite often. Have you ever watched The Flash on CW? Oh my God.
But you watch it anyway, right?
I watch it anyway, but oh my God. Wait, I just laugh at the stuff they're saying. That's a particularly egregious example,
Yeah.
but there's lots of other ones.
Speaking of that kind of thing, how might a fantasy writer use particle physics to do some sort of fresh, unique world building or come up with some fantastic story idea?
I was reading stuff for this year's Hugo Awards, and one of the Hugo nominated novellas is A Spindle Splintered by Alex Harrow. And this is a reimagining of Sleeping Beauty. Okay, so you would not expect to find physics in this, but there was. She has, this is a bit of a spoiler, she has a multiverse in there. And she talks about laws of physics and blah, blah, blah. So that's one example of working things into a fantasy. And I don't know, people here may have other better examples of working, sciencey stuff into a fantasy.
I don't have a piece of art to point to, but I was going to ask a similar question to what Chris asked. I think the presence or absence of magic and the removal of magic from a fantasy world could correlate very nicely to the change of physics laws.
Right.
You could really make a nice metaphor for that.
Right.
Scientifically removing magic from a system and seeing what the consequences are. I think it'd be cool.
Yeah, I'm blanking on Matthew Hughes, who does the stuff that's very Jack Vancian. He had a whole series where it's like science was on the decline and magic was on the rise, and that the stories were placed in this sort of uncomfortable intersection of the two, and that was a lot of fun.
So I have a funky question.
Yeah.
If you could be tiny enough to see the Higgs field, what do you imagine it looks like?
That's a good question. I mean, that's kind of taking me to Ant-Man or the Atom, where he'll shrink down in the comics to subatomic size, and that's generally just visualized as a bunch of lines and dots and pretty colors and stuff. It's probably not that, I would think, but then there's the whole question of, you would have to be seeing with something other than light, because you're not going to be seeing in the way that you see at those sorts of scales. That's a wonderful question for the imagination. What senses would you be using? How would it feel to you? I don't know. Write a story. Tell me.
What are your thoughts on the concepts of like fifth, sixth, seventh states of matter? Like, I don't know if you've seen something recently about information being one of these. What would it even mean if information were a state of matter?
The people connect information with entropy in ways that I didn't take enough statistical mechanics to understand. But it is, and people talk about information being lost or not in black holes. So I'm not sure, again, this may just be my ignorance, that there's a universally agreed on definition of information in a physics sense. But, people like Hawking and others and some statistical mechanics people have used information in some statistical sense. That, again, if there's any theorists in the audience that know better than me, please speak up. But yeah, that's a really interesting question, and it's definitely something that there's work being done on. I just am ignorant of that work.
We're getting close to time. We should get out of here. Does anybody else have any questions? All right. There's one thing I wanted to ask you, Phil, that you talked about dark matter and dark energy. Could you talk a little bit about other exotic matter like antimatter?
Okay. So I had antimatter in the first version of this talk, but it didn't really fit. Probably people here know that for every bit of matter, there's a corresponding antimatter counterpart. Star Trek didn't make up antimatter. It's a real thing. And if you had enough antimatter, yeah, you could power your starship that way, because when antimatter meets matter, it creates energy. So I had on the bottom of this slide, E equals mc squared. When a matter particle meets its antimatter counterpart, it turns into energy, usually in the form of gamma rays, but then that energy would be available for doing what you want. It also works the other way. You can take pure energy and turn it into matter. That's part of what we do in these colliders. And the rule in particle physics is if I'm going to make a matter particle like an electron, I also have to make the corresponding antimatter particle, which is called a positron. So if I'm going to make an electron, I also have to make a positron. This leads to another huge problem in particle physics, which is, okay, the rules of particle physics say the universe starts with a certain amount of energy. Energy ought to turn into equal parts matter and antimatter. But when you look at the universe, it's overwhelmingly matter. We do not see very much antimatter out there, so what gives? And there's lots of ideas about that, but we don't think there's like antimatter planets and galaxies out there. Why not? This is a big disappointment to readers of Green Lantern comics, where you may know one of the bad guys is from an antimatter planet called Quard. This is from an old Green Lantern comic. An antimatter universe occupying the same space-time continuum as yours, but on a different space-time level. I have no idea what that means, but at least they're acknowledging that there probably isn't an antimatter planet out there unless you do some hocus pocus. But yeah, what happened to all the antimatter is one of the big questions in particle physics and cosmology. But it's a real thing.
Would it even be like visible and observational?
What would be visible would be when matter and antimatter collided. Then you'd see all these gamma rays being produced from their annihilation. And of course, astronomers look for this and they're not seeing it, which, if there were, like, it's antimatter over there, it's matter over here on the boundary, you would see all this action happening.
So if there were an antimatter star out there,
right,
we wouldn't know unless something hit that star.
Right. You wouldn't know unless something hit it. Yeah. But it'd have to be like really isolated where we couldn't see, like the boundary with the rest of the matter universe.
Some more fertile ground for writers, is it?
Absolutely.
All right. Well, we should probably shut down here so the library folks can get home.
Library is very good at kicking us out at 8. I've learned that.
Thank you, Phil, so much.
Thank you.
For being our inaugural Ad Astra Presents talk, our speaker.
Hope this was fun for y'all.
And thank you all so much for coming, and those of you online for joining us. Hope to see some of you in our future events. And